So for the higher tier here, we have to bear three things in mind. They are solid inelastic spheres and have no forces between them. Now again, GCSE Science here is actually fairly advanced, but not that you'd know it, because there is something called an ideal gas. And that pretty much describes an ideal gas. And there's an ideal gas law. And the ideal gas law, not that you need to know it again, looks like this. If you've ever come across something looking like that, PV equals nRT. And it describes how gases behave. There are actually three different propositions in there, all of which are on their own are laws themselves, like Charles' law, Boyle's law, and Avogadro's law. And basically, ideal gases, or most gases, behave like ideal gases. That means they behave as if they are solid inelastic spheres. So these are actually two different things, well, two things that describe different properties but have different demands. So the fact that they're all spherical, they all behave like spheres. Of course, we know that that is not the case, as I said about carbon dioxide, for example. It's not, and hydrogen and oxygen and virtually every gas apart from the noble gases aren't completely spherical. And the fact that they are solid and inelastic means not that they are a solid, as in a solid liquid or a gas, but that when they collide, they don't deform, for example. And again, for us, that's not much of a problem. But when you talk about their behavior in a model, they don't behave like billiard balls, where one crashes into another and then the other one moves off and the second one moves away with like half the velocity and the first one goes forward with half the velocity. So they are not completely inelastic in terms of their collisions. And thirdly, they have no forces between them. And as I've said now a few times, they have van der Waals forces between them. And that means there are actually small forces of attraction. And that is expressed by their boiling points. So if you've got a gas like carbon dioxide does not behave like an ideal gas over a large amount or a large range of temperatures. And it is actually solidified fairly easily at minus 78 degrees centigrade. Don't quote me on that. But then you can have a solid. Whereas nitrogen and oxygen take temperatures that are a lot lower before they become a liquid. Ammonia again is a gas at room temperature, but it's easily solidified at lower temperatures. So these interactions depend very much on what the gases are made out of, and our assumption that there are no forces between them is a limitation of this model. But for most gases at room temperature and standard pressure, it really doesn't matter. So we can treat them as solid inelastic spheres with no forces between them.
Please like and subscribe and let me know of any questions you'd like me to cover in the comments.